what is the next step? So where have been? We have been calculating the point estimators of population parameters, mean, variance, etc., that is x bar equivalent point estimators. Use the sample distribution, that is for x bar it is use central limit theorem or make the assumption of underlying is Gaussian and do either a normal distribution or t distribution to assess the reliability of an estimate. So what is the confidence interval we have given? We have basically assessed the reliability of the estimate through confidence interval. This is what we have done so far, right. So we have estimated point parameters and then we have given confidence intervals as a reliability of the estimate. So confidence interval is nothing but reliability of the estimate. So the reliability of the estimate will obviously poor if you use lesser number of samples, and it will get better and better if you increase the number of samples, right. So that is why if you toss a coin 10 times, 8 times you get a head and 2 times you get a tail, your proportion is what? 0.2 is for tail and 0.8 for head, your proportion. But if you see this proportion is good, so there is nothing wrong with the data, that is what it tells you, right. So you say 0.8 is a good estimator, is an estimator for true p, true proportion. Your p hat is what? 0.8, your true p you do not know, let us assume you do not know the true p, your p hat is 0.8, right, for tossing of a coin. Although we know the true p, if you do this p hat is 0.8, what is bothering us? The reliability of the estimate. So with 10 samples, if you do p hat plus or minus confidence interval, that will blow up, the range will blow up, okay. The range will not be tighter, the range will blow up. Use the z alpha by 2, you will p hat plus or minus sigma pq by n into, use that z alpha by 2, it will blow up. Now if you want to bring it tighter and tighter, then you have to do more experiments, and obviously if you do more and more tossing of a coin, what will you end up with? Probability, you will close to 0.5, you will start coming close to 0.5, that is the idea, right. So that is where little samples does not make sense, okay. Where are we going? So now next step, what is the obvious next step? We have given estimators, point estimators for, so what have we started with? Started with sample data, and then we have built a statistic which is a estimate of population parameter, and then we gave reliability measure or reliability for the point estimate. Now what is the next step? So now in a sense we have used point estimate, we are ready to use point estimate along with its reliability as a inference for underlying population. So this is where we are heading to, we are now going to do inferential statistics, right. So now we have established the fact that my point estimators like x bar, proportions, we have not covered variance, we will cover variance also. So at least x bar and proportions as a reliable estimate, the reliability varies depending upon n, as an estimate of the underlying population mean. Now can I use this to solve certain problems, okay, can I use this to really test hypothesis? Basically can I infer about the underlying population using the sample estimate, okay. So that is what we are heading to, okay. So that is where we talk about what is called as hypothesis testing, okay. So we are now going to talk about hypothesis testing, okay. So the hypothesis testing overall idea, the key simple argument to give, have you seen what are the judgment, how much pages will the judgment report be, an Indian court judge report, whether you want to be given a credit card or not, it is a common question, financial marketing, the financial domain, right. How do I give you assess whether you should be given a credit card or not. How is credit score, only credit score, how is it calculated? So your bank statements, right, your bank statements, your, that will give you the overall credit, debit, etc. Then I say that this person's average is above my threshold that I set for giving a credit card. Is it? If I go back and look at the data and then say is it worth it or not, then I can understand, right. So many sectors when you talk about, so again the quality control is a classic example. Whether I should, in India Tirupur is known to export, Tamil Nadu, Tirupur is known to be a big exporter of what? Garments, right, it is a big exporter of garments. Now I send in garments from the factory and a quality control engineer has to check whether it meets the standard or not. Obviously he cannot open up every batch. Why? Very heavy, time consuming, it is a big time consuming exercise. You are not going to export one batch with 100, you are talking about in multiple thousands or if not in millions. I cannot open the batches and check everything, that is a very time consuming exercise. And remember the test you want to do to check will take money and cost, will take money and time, and that will not be borne by the factory, that will be borne by the guy who is receiving it, right. So he has to obviously make a he has to make a call with samples, not the entire population, like your Alfonso mango case. I was talking Europe rejected Alfonso mangoes, right. So the same case, how do I do it? Now what is the question, what is the question how do we go about solving this problem? This is a qualitative statement, how do I do it quantitatively? In garments at least, in garments what is something which is very critical? That is quality, is again a qualitative statement. Color, right, shade, okay, shade I can test for. The thread count, it is very important. Visible defects, the thread count, right. So the thread count is pretty important, visible defects in the thread count, so many of them, right. There are certain parameters for a garment that has to be met. Now what is the statement I can make, how do I again make it mathematical? These are the parameters I have to check for. Let us take one, let us take simple thread count. What is the thread count the user would have claimed, I mean the exporter would have claimed? Certain number, right. What is it I want to check? Now if I sample, my average thread count should be what? I should be sure that the true mean mu, right, let us make this little better. I should be sure when I send the true population mu in mu should be within a certain bound with high percentage of accuracy. So always there will be error tolerance allowed, that is what standard error is. So you have, this is where this thing becomes, n becomes important. You have the standard error allowed, let us say you have let us say 22 or 20 as the thread count, whatever 100 as the thread count, 100 plus or minus is allowed. Now I want to make sure whether the underlying population also has the 100 plus or minus thread count with what percentage of accuracy, that is determined by you, 95 or 99 percentage of accuracy. So if I want to put it in a testing way, I would say as a qualitative engineer, quality control engineer, what would I do? Begin with what? As a quality control engineer, if I look at the thread garments, what will I begin with? Will I begin with it can be acceptable or it is not acceptable? I will begin with saying this does not meet my standards, okay. I will begin with a statement, this does not meet my standards. In a court, what is the statement with which, what is the hypothesis with which the judge will look at the convict or the one who is in the one who is convicted, what is the thing? Innocent until proven guilty. That is the status quo. Okay. So the status quo for garment export is, it is not accepted. Status quo, you have not accepted it, right? Status quo. So usually the null hypothesis is always the status quo. Null hypothesis is always the status quo, right. So that means whatever continues, whatever is there continues. So in export I have not accepted it. So what is the status? It is not fit, right. So the status quo is always the null hypothesis. Clear everybody? Let us be very clear, because making important, null hypothesis is the important thing. Okay. Once you make the null hypothesis, the alternate hypothesis is what? We never claim, see these statements are very important technically, we never claim something to be true or something to be false, we never do that. What we say, look at this, alternate hypothesis is supported if the data provides sufficient evidence. So if we say there is enough evidence to prove that the alternate hypothesis is, or the status quo is not correct. What do we say? We only say the alternate hypothesis is supported if the data provides sufficient evidence. Okay. True, nobody can claim this is correct or this is the truth. Okay. The data is suggested, so that is where this thing, the data, there is enough evidence to prove that he is guilty. There is not enough evidence to prove that he is guilty. You have seen the statements, right? The quote, there will be always, there is enough evidence to prove that he is guilty, or there is not enough evidence to prove him guilty, and therefore status quo continues. Clear? So I have a null hypothesis which is what I am interested in. So when in a case like if you go to the in the court scenes, if you would have seen the movies etc., what will be the lawyer trying to do, appointed by the government? He will be trying to prove that the convict is guilty, and the defense lawyer will be actually opposing it, right. The government's job, the government lawyer will be trying to prove that he is guilty. For him, what is the null hypothesis? He is not guilty, right, and he is trying to prove that he is guilty, and that is where the judgment also comes from. The judgment also is, there is no evidence to prove that he is guilty, or there is enough evidence to prove that he is guilty. So null hypothesis is something which you always want to reject. Null hypothesis is status quo, and that is what you want to reject. Alternate hypothesis is what you want to happen. Okay, and if you want alternate hypothesis to happen, what should be my alpha value, or what should be my confidence? If you want to change status quo, you should be very much confident. Okay, if you want to change, so that is why choosing null and alternate hypothesis is very important. Okay, because if you want very heavy high evidence data to change the status quo, that means you should be very high confident. Okay, whereas null hypothesis, you are not testing for null hypothesis, you are wanting to prove the alternate hypothesis that is correct. So you have to give more and more confidence, you should be more and more confident that alternate hypothesis is correct, or you can reject null hypothesis. Clear? So you should be highly confident to reject the null hypothesis. That means your alpha should be very very small. Okay, clear? Your alpha should be very very small. Therefore 1 minus alpha is very high. That means what? If alpha is very small, what will happen in the court? Okay, court situation. I say alpha is 0.001. What does it mean? You need to prove that you need to reject null hypothesis with very high confidence. That means there is an error of what? There is an error of accepting a person to be not guilty even though he is guilty. You understand? There is an error of accepting the person to be, you understand what is it? There are two kinds of errors, right. So in this case itself there are two kinds of errors. Can you tell me what is it? So not guilty, data suggests that he is guilty. What are the two kinds of errors? So we have guilty, I am taking numerical, non-numerical so that you understand. So this is what you concluded, this is the truth. So no error, right. Person is guilty, you have found out to be, you have concluded to be guilty, and not guilty, no error. What is this? Truly he is guilty, but you say not guilty. What does it mean? When will that happen? Truly he is guilty, but you declare that he is not guilty. When will that happen? There is not enough evidence to prove. So what is that error? How much is that error? That is tricky, so let us come back. So how about this? He is not guilty, but you have told him to be guilty. When will that happen? He is not guilty, but you have told him to be guilty. That is, alternate hypothesis is correct, even though null hypothesis, truth is null hypothesis, but you have concluded it to be alternate hypothesis. What is that error? Is it small or is it large? Large. Think about it, you understand the question? Not guilty is what? Is your status quo, you have rejected the status quo erroneously. What is the error? What is that value? You know the value also. What is that error? You have rejected the null hypothesis even though it is correct. Alpha. That is the percentage with which you can actually reject the null hypothesis even though it is correct. That is why he said alpha. Alpha is the error in rejecting the null hypothesis even though it is correct, right. So what are you saying? I am 99% sure that the mu lies within this bounds. What is uncertain? 1%, right. So what is the error? Alpha 0.05 or 0.01, 1% is what? 0.01, that is the error. So this error is also called as what? Type 1 error. If you put this way, not guilty, and then this is guilty, okay, and then you say concluded truth. Not guilty, but you are declaring him to be guilty is alpha. This is called type 1 error. It is also called as type 1 error because you have rejected the null hypothesis even though it is correct. You have rejected the null hypothesis even though it is corrected. You have declared it to be guilty even though he is not guilty. How much percentage you are doing? You are already 99% sure, that means you are only 1% unsure, which is nothing but alpha 0.01. Clear? So that is called type 1 error. And there is another error. What is this? This we call it as beta, which is type 2 error. Beta is my type 2 error. What is beta? Your null hypothesis is false, okay, but you are accepting, right. This is my null hypothesis. this is my alternate. So I can even redraw the table, okay, null alternate. So H naught H A H naught H A, no error, no error. This is my truth, concluded. So no error. This is alpha, truth is alpha, H naught, you have accepted H A, that is my alpha. Truth is H A, but you have concluded H naught, that is you are not able to reject the null hypothesis even though it is not correct, that is beta. This is type 1 error, type 1, and this is type 2. What is the relation between type 1 and type 2? Do you see a relation between type 1 error and type 2 error? They are competing, right. If you have alpha to be very low, that is if you have allowed type 1 error, then what are you going to do? You will most likely reject the null hypothesis because your type 1 error is higher. That is you want to be only 50% sure or 70% sure. That means you are allowing for more error, but that also means that you are going to reject the null hypothesis more number of times. So type 2 error will decrease. If your type 1 error is decreases, that means you are having a more probability of accepting null hypothesis. So type 2 error will increase. So this alpha and beta are actually competing, right. So the question is not about trading off together, because you know that this cannot be traded off. Alpha and beta are always going to compete. If you increase alpha, beta will decrease. If you decrease alpha, beta will increase. So there is no question about it. So now the question is, that is where we find, that is why I initially wanted to introduce all these elements. You are fixing alpha, you are fixing alpha. Now for a fixed alpha, how do I bring beta down? That is the question we will be asking, right. We will not be playing with both the parameters, which is not making sense. So we will fix alpha and then say how do I bring beta down, okay. That is the question we will answer. Beta do we know right now? Beta value is known to me now. Is beta 1 minus alpha? Is beta is 1 minus alpha? If beta is 1 minus alpha, the half diagonals add to 100, then there is no diagonal at all. That means you will never make a correct decision. So beta cannot be 1 minus alpha. You understand? No, most often people mistake, okay, alpha is type 1 error, then beta has to be 1 minus alpha, which is type 2. No, if you add beta and alpha, the half diagonal itself makes up to 100%. So you will never make a correct decision if you have beta to be 1 minus alpha, okay. So beta, to calculate beta you should know the truth, because you are saying that null is, you are rejecting, you are accepting null even though if it is not correct. So then you need to know the value of the null or value of the truth, okay. Only when you know the truth, beta can be calculated, okay. Alpha is you fix it, beta can be calculated only when you know the ground truth, because you are saying I will reject, I will accept null even though if it is false. But what is false? How much I am? Suppose the truth is, suppose your truth is 50 and you are concluding your null is 50.1, okay. So what am I saying? Your, let us say your alternate hypothesis is this thing, the truth, right. I mean beta is type 2 error. So what are we saying? You accept H naught is null, you have concluded to be alternate, okay, fine. H, okay, H naught is, this is the concluded, you concluded even though if it is false, even though it is false. Now your null hypothesis, mean equals to 50, okay. Null, your mu or mu is 50, okay. Estimated, your mu is x bar is what, 50.1, 50.2, okay, and your standard error is only 0.1, very small. That means what, you want to distinguish between 50 and 50.2, very small numbers, then obviously beta will be high. Why? You are allowing for very small difference between the, you are having a very tight bound for underlying population mu. If your bound is large, then beta will be small, you understand. If you want to distinguish between two numbers, let us say 50 and 50.2, that means your bound should be very small, your bound is mu equals to x bar plus or minus 0.1, that bound is very tight, okay. Suppose your bound is like mu equals to x bar plus or minus 10, then beta will be obviously lower, because you want to distinguish two things which are very far apart. But if you want to distinguish which are two things which are very small, that is your bounds are very tight, then beta will go high. It all makes sense, right. So in a sense, what am I saying, if you want to be very sure and at the same time you want to be very sure about the tightest bounds on the population parameter, then there is a very high chance that you will make a error, okay. That is all I am saying. If you want to be very sure, that is alpha high, and very sure about what, the population parameter with very tight bounds, obviously beta will be high. If the bounds are relaxed, beta will go down. If your alpha is relaxed, beta will go down. But in general, what do? We cannot compromise on both alpha and what, your bounds also. You want the bounds to be smaller, you cannot compromise on alpha, so beta will be generally high. Beta's range is typically a very good method, I mean no statistical method, a very good method will have a beta of around 0.2, 20%. That means 20% of the time I will accept null hypothesis even though it is wrong. That is why, and in the court of law it all makes sense. The court of law says what, I cannot punish a person, even if I can let go of many persons who are guilty, I cannot punish one innocent. So that itself says you can have beta to be higher, but alpha has to be as small as possible, right. Now if you want alpha for a fixed alpha, if you want beta to be down, what will you do? How can you achieve that? You want alpha to be small but also beta to be small. How do you do that? The standard error bound, right, that has to be tight, means what will increase? Evidence should increase. It all points out to one direction, the evidence should increase, okay. So that is where the regular paper and papers which make in Nature or in New England Journal of Medicine etc., the evidence should be large enough, okay, to make conclusions. So this is the elements of a hypothesis, and if the test statistics has a high probability, so how do I test? I have a test statistic, that is usually my what, x bar. If the test statistic has a high probability when H naught is true, then H naught is not rejected. If the test statistic has a very low probability when H naught is true, then H naught is rejected. We are only accepting or rejecting null hypothesis. We are never claiming the alternate hypothesis is right. We are only rejecting the status quo or accepting the status quo, okay. If your test statistic has a high probability that this underlying distribution of the data has come from the null hypothesis, then you say that the status quo is preserved. That means if your x bar closely resembles your mu naught within the standard error, then you say that the null hypothesis is true. If your x bar is not closely resembling the mu naught within the standard error for certain accurate, certain percentage of confidence, then you say that H naught is rejected. Make sense?
Is it possible for us to convert any qualitative study into quantitative?
It depends on parameters what you look for. The basic key idea is what? That is where we started off. What did we do? We started off defining random variable. What is the definition of random variable? You map all the qualitative outcomes to onto a real number. Exactly. You can make color. So you see earlier you used to do what? In Netflix, before Netflix, if you say good, bad, this thing. Now what are they giving you? Rating. Even customer rating, what are they giving you? They are giving you numbers. They made it to be categorical 0 to 9. Your movie ratings become 0 to 5 stars, 4.5 stars. If you look at Amazon, you will get 4.5 stars. Convert it to numbers, right? Irrespective of the domain, it is possible to assign numbers so that you can convert it into a quantitative problem. That is the definition of a random variable. If you are able to define random variables, then you are already in numerical domain. That is why we started off with random variables. That is the idea.
So in the present judgment that is being made, the statistics
Obviously will play a role. That is why you have to look at the reports. What is it they are doing? I have not seen a report, full report. There will be evidence, there will be calculations that has to be done. You cannot just do it all in a thin air, play with human life, right?
So you were saying like evidence are very important and it should be right.
Evidence are very important, so you have to assign fact weights. You have to assign weights to each of them. See, look at your annual credit statement. So let us take, you give a loan to a company, a startup company. What do you look for? Annual bank statements, annual expenditure reports, annual statements. You think company's annual statements, everything is numbers? No, there will be stakes, everything that has to be looked at, converted. Either you do it systematically using this hypothesis testing, or you do it subjectivity, but those points actually mentally you are doing the same thing. Okay, whether every domain has translated into a statistical thing, I do not know. You see what I am saying? This is what mentally also you do in many domains. But if you ask me a question whether all domains have embraced this data science and then taken an approach to systematically do it, I do not know the answer. Maybe not.
What about the domain of law?
That is what I am saying. Maybe no, I do not know, maybe not. See, today you can actually give associate. So even today, I was working, recently started doing this annual bank statement, expenditures, etc. So when we look at people, there are keywords to capture whether it is a credit, whether it is a debit in a report, and then translate it to numbers, appropriate numbers. So the same way weightages have to be given, right? Whether it is done or not, we do not know. That is what the key is.
It will be beneficial if we do it.
Of course, it will give a scientific way of concluding things.
And easy as well.
Easy, I do not know how much effort is required to convert it, but it will give you a scientific approach to solve things.
So again we make the evidence as a individual.
You have to continue to do it as a random variable, continue transform it into a contestant.
In terms of probability.
Yes. So this is what we talk about, elements of test hypothesis. You have, now you have two regions. One, this is my rejection region, acceptance region, this part is my acceptance, and this is my rejection. This is acceptance of H naught. What is it? Mu x bar minus z alpha by 2 into sigma over root n, x bar plus z alpha by 2 into sigma over root n. So this region you accept. Why? Because you are saying the mu, it is in the bounds of the original mu naught, so you accept it. Anything beyond it, you start rejecting. That is when you reject the status quo. So this is where your acceptance region, which is mu equals to x bar plus or minus z alpha by 2 into sigma over root n, which is your confidence interval basically. If mu lies within your confidence interval, you accept it, and if mu is beyond the confidence interval, if your x bar or whatever you calculate is beyond this bounds, then you reject the null hypothesis. Clear? So clear what is acceptance and rejectance? It is basically the bounds. Okay, so you have bounds for mu, okay, and if your x bar is within this bounds, you are only calculating x bar, you are not calculating mu, you are estimating mu using x bar. So you have assumed a mean mu, this is my mu naught, let us assume null hypothesis mu naught, h naught, okay. Now my x bar lies within these bounds, then what do? I calculate from data, and my data, my x bar lies within this. In this case you are actually calculating only x bar, mu naught is given to you. Now x bar is something within this region. What is the region? Mu naught plus or minus, mu naught x bar plus or minus z alpha by 2 into sigma over root n. If that is the region within which the x bar lies, then you say perfect, okay. Or if you have to say my x bar, whatever you calculate x bar is what? Mu naught plus or minus z alpha by 2 into sigma over root n, then you say you accept the null hypothesis, right, because you are calculating x bar from the data, you have assumed a mu naught, and you know this is what the bounds I want for 95% confidence, and if your x bar lies within that bounds, then typically mu naught is right. If it is beyond the bounds, only then say no, it is not right, I reject the null hypothesis. Make sense? So this is the table which we discussed, okay. So these are the elements, and then from next class onwards we will start doing some problems, tomorrow's class, okay. Thank you folks.